For a little while now, it's been hotly debated that the object that kicked off the Cretaceous-Paleogene extinction was most likely a comet that originated from the Oort cloud rather than an asteroid from the asteroid belt. And while large objects definitely do come from the Oort cloud, with the discovery of comet Bernardinelli-Bernstein that we reported on recently proving this without a shadow of a doubt, this is a relatively rare phenomenon. Most of the evidence concerning the identity of the Chicxulub impactor found since the 1980s has pointed toward it having been an asteroid, though some anomalies in the crater left behind by the impactor 66 million years ago have also suggested cometary properties as well. So which is it, comet or asteroid? And regardless of composition, where did it come from? Could a similar object spell doom for us in the future? And if so, how long do we have? Well, we may finally have a definitive answer for all of those questions. But the actual location of the object that initiated the removal of all non-avian dinosaurs may surprise you, because it's not the Oort cloud after all. Before we jump in, be sure to do the thing and like, comment, join the mailing list, and smash that subscribe button. I'm Eric Malachite, author of Echoes of Olympus Mons, and this is Science Get. In February of this year, a new theory was proposed about the impactor that initiated a chain reaction that led to the extinction of all non-avian dinosaurs on planet Earth 66 million years ago. Now, the impactor theory has been the leading explanation for the disappearance of the dinosaurs since the 1980s, beating out other theories like increased volcanic activity and dinosaur farts. Yes, that's a real theory. But figuring out where that impactor came from has been a major challenge. Even scientists at NASA, who are tasked with scanning the skies for potential threats to the Earth, have been unable to pinpoint where the object that formed the Chicxulub crater in the Yucatan Peninsula came from. This past February, in a study published in the journal Scientific Reports, a group of scientists proposed that the impactor wasn't an asteroid at all, but rather a fragment of a comet that flew too close to the Sun after having its orbit altered by Jupiter. That comet would have come from the Oort cloud, a shell of material that surrounds the solar system and is composed primarily of comets and dwarf planets like Pluto. The Oort cloud contains at least 1 trillion icy objects. H.P. Lovecraft once said that the oldest and strongest emotion of mankind is fear, and the oldest and strongest fear is the fear of the unknown. We really don't know much about the Oort cloud. Comet Bernardinelli-Bernstein is going to be the closest we'll get to an object originating from that region for a very long time, so it's easy to see why this would be a tempting thought. Most of the objects in the Oort cloud have orbits that can take hundreds or even thousands of years to complete, but occasionally massive planets like Jupiter can cause disruptions in their orbits. The solar system is basically a pinball map for these kinds of objects. Back in 2013, a group of researchers from Dartmouth College also suggested that a comet moving at high speed could have created the Chicxulub crater. The impactor that made the crater was moving almost 20 kilometers a second when it slammed into the Earth. A blistering speed by anyone's standards, literally, as you're about to find out. The initial explosion released at least 10 billion times the power of the atomic bombs dropped on Hiroshima and Nagasaki. It also created wildfires all across the Americas, 1.6 kilometer tall tidal waves, and released a ton of sulfur into the atmosphere. But even back in February, some researchers were casting doubts on this possibility. Natalia Artemyeva, a senior scientist at the Planetary Science Institute in Arizona, told the New York Times that cometary fragments from an Oort cloud object getting too close to the Sun would have been too small to create the Chicxulub crater, which is nearly 180 kilometers in diameter. I wonder what she'd say now that we've discovered one with a possible diameter of 100 kilometers. While existing evidence has always favored the idea that Chicxulub was an asteroid, it has not been 100% conclusive, and Artemyeva says that there is some wiggle room, and that's in the form of a type of material that's also found in craters in South Africa and Kazakhstan as well. And that substance is carbonaceous chondrite, a substance that is found in a wide swath of comets, but only about 10% of asteroids seem to be composed of the stuff. More on this stuff later. But iridium is also found in the Chicxulub crater, most of it found within a 5-centimeter section of the rock core that was retrieved from the top of the crater's peak ring, a region of Chicxulub that reaches a high elevation that was created when rocks rebounded before collapsing from the immense force of the impact event. Analysis of that iridium was carried out by labs in Austria, Belgium, Japan, and the United States. But iridium was not the only material common to asteroids that was found in the crater. In fact, there is a layer in the geological record that dates back to the same time period of the Chicxulub impact and contains very similar elements. Remember when we mentioned that sulfur was also kicked into the atmosphere during the impact? Well, they also found sulfurous elements in that core sample, though a 2019 study found that sulfur-bearing rocks are missing from the rest of the core, despite being present in large volumes in the surrounding limestone, which suggests that the original sulfur was blasted up into our atmosphere. Sulfur getting kicked into the atmosphere in this way made the impact event much worse, as it exacerbated global cooling effects and led to acid rain. According to the study from February of this year, though, only 2 to 3 objects from the Oort cloud could have hit the Earth during the last 500 million years, contrasting another study that suggested that the Earth is impacted by Chicxulub-sized asteroids every 100 million years or so. So why do we think that the impactor was definitively an asteroid? Let's find out. The massive 10-kilometer, 6-mile wide asteroid that spelled certain doom for 75% of all life on Earth 66 million years ago, ushering in the series of events that make up the Cretaceous-Paleogene extinction event, has been thoroughly investigated at last. Based on data from all of the known impacts our planet has experienced in the past, researchers have been using a combination of computer modeling and theoretical analysis to pin down exactly where the Chicxulub impactor might have come from. This image represents the orbits of the inner planets and Jupiter. The bright green dots represent asteroids and a dwarf planet called Ceres that hang out in largely stable orbits between Mars and Jupiter. The red dots are asteroids that have broken off from the asteroid belt and are considered to have at least some chance of hitting the Earth at some point in the future. The asteroid belt is located more than 2.5 times the average distance from the Sun to the Earth. It's home to millions of asteroids with an average distance between objects equal to 1 million kilometers, or 600,000 miles. In recent years, researchers have suggested that the asteroid belt does not typically send extinction-level impactors toward our planet, until now. Believe it or not, the result of those extensive studies, computer and theoretical models have told researchers that the asteroid that killed the dinosaurs more than likely came from the asteroid belt. In fact, based off of these new models, scientists at the Southwest Research Institute have come to the conclusion that large impacts from asteroids in the outer half of the asteroid belt between Mars and Jupiter occur at least 10 times more frequently than we previously thought. This could also mean that previous studies that suggested that the object that smashed into Mexico's Yucatan Peninsula 66 million years ago was a comet are wrong. Though some of the objects in the asteroid belt do exhibit cometary properties, so there still could be a bit of truth in those studies. So I guess there is equal probability that either is true. Or is there? Well, core samples from the 144-kilometer diameter Chicxulub crater have shown that the impactor more than likely featured a composition similar to carbonaceous chondrite meteorites. While these types of meteorites are pretty common, none that we know of today are large enough to cause a disaster on the level of what happened 66 million years ago. You might be scratching your head wondering how this substance could be used as evidence for the asteroid hypothesis and the comet hypothesis, and I don't blame you, but hold that thought. David Nesvorny, lead author of the paper describing the research in the journal Icarus, says, "We decided to look for where the siblings of the Chicxulub impactor might be hiding." Siblings? Well, that sounds pretty ominous. Could the dinosaur killer really have a sister out there somewhere? And could computer models really show us where it is? Nesvorny and his team used NASA's Pleiades supercomputer to track the trajectories of 130,000 simulated objects in the asteroid belt. The computer models focused on thermal forces that are thought to nudge bodies into orbits that could send them hurtling out of the belt, otherwise known as escape hatches, and into orbits that could intersect with Earth's. The team was shocked to find that 10-kilometer wide asteroids end up in the outer region of the belt at least 10 times more often than we previously thought. Essentially, this means that every 250 million years, give or take, One of these things ends up in the outer region of the belt. Co-author Simone Marchi says, "This result is intriguing not only because the outer half of the asteroid belt is home to large numbers of carbonaceous chondrite impactors, but also because the team simulations can, for the first time, reproduce the orbits of large asteroids on the verge of approaching Earth. Our explanation for the source of the Chicxulub impactor fits in beautifully with what we already know about how asteroids evolve." So there it is, folks, the reason why carbonaceous chondrite could be used as evidence for both hypotheses. Before, it seemed like larger asteroids composed of this substance were very rare, and to be fair, they still are. But with these models, we now know that they end up in orbits intersecting the Earth's far more often than we thought, which is fascinating. If these simulations prove to stand the test of time, then I suppose the mystery of where and what type of object the Chicxulub impactor was has finally been solved. And at the same time, I guess we'll be safe from Chicxulub-sized asteroids for the next 184 million years, hopefully. If you dug this content, be sure to drop me a like and comment down below what you think of this study. Do you think this simulation proves without a shadow of a doubt that the object came from the asteroid belt? And be sure to smash that subscribe button, ring that bell to never miss an episode of the show, and check out the Patreon while you're at it. Speaking of which, look at all those wonderful names. Thank you, patrons. I'm Eric Malachite, and I'll see you next time.